55 gallons is the exact internal capacity of a standard industrial steel drum that can remain in active service for more than 20 years. Why can such a common container withstand harsh chemicals, high internal pressure, and repeated heavy impacts while maintaining a perfectly airtight seal? It only looks obvious that a metal cylinder would be durable, but in reality, its longevity depends on a sophisticated engineering chain that transforms raw sheets into high-strength vessels. This technical evolution involves multiple stages of material preparation, precision body forming, and reinforced welding to ensure structural integrity under extreme conditions. Everything only gets more complicated as the production line progresses through reinforcing, coating, and testing. One can notice how the process begins with the preparation of industrial-grade steel sheets, which are cut and fed into forming machines with millisecond synchronization. The equipment gradually curves the metal into a perfect cylinder before the longitudinal seam is fused by high-frequency precision welding. But this is just the beginning. It seems simple to just weld a seam, but in reality, the weld must be as strong as the base metal itself to prevent any leakage during decades of transport. The body then moves to the flanging station, where the edges are bent to prepare for the attachment of the top and bottom discs. At first glance, the drum body appears finished, but it lacks the structural rigidity needed to survive stacking in warehouses. This is where the rolling of reinforcing ribs occurs, as heavy hydraulic rollers press into the spinning metal to create deep horizontal ridges. It is visible how the steel deforms under controlled pressure, gaining the necessary stiffness to resist buckling under the weight of 300 tons of stacked cargo. The process is only gaining momentum. Automated manipulators then position the circular lids onto the flanged body for the seaming process. 7 layers of metal are folded together in a tight mechanical interlocking joint known as a double seam, which is compressed until the seal is hermetically closed without the use of adhesives. One can notice how the rollers move in a circular path, exerting tons of pressure to fuse the components into a single unit. The drum then undergoes a series of rigorous safety inspections, where internal air pressure is applied to detect even microscopic failures in the joints. Following successful validation, the containers enter the cleaning and coating chambers, where specialized chemicals strip away oils before a protective layer is applied. The camera glides along the automated line as the drums are rotated and sprayed with industrial-grade finishes that prevent corrosion from both the environment and the internal contents. Thus, the steel reaches the standard ready for the further stage of shipping and global logistics. 100 million steel drums emerge from production lines every single year. Why is this specific industrial container manufactured at such a relentless pace? 3 new units appear every second to support the chemical, oil, gas, food, and pharmaceutical industries. This volume ensures that global logistics chains never face a shortage of reliable transport vessels. Revenue from this sector has already surpassed $12 billion annually. The growth persists because global demand for safe hazardous material transport increases alongside industrial expansion. It only looks obvious to treat these containers as disposable packaging, but in reality, their engineering serves a much longer life cycle. One can notice how the structural integrity of the steel allows for rigorous repeated use. But this is just the beginning. Steel drums are not a single-use product. They rank among the most frequently reused steel objects in the modern industrial landscape. This cycle of recovery and refurbishment turns a simple cylindrical vessel into a sophisticated engineering link. It is visible how the metal maintains its shape and seal through hundreds of transit cycles across the global supply chain. The process is only gaining momentum as companies prioritize the recovery of these assets. This near-limitless cycle of reuse elevates the container from a commodity into an indispensable economic tool. From the primary manufacturing floor to the final logistics hub, the steel drum functions as a permanent component of international trade. Everything only gets more complicated as the engineering requirements for these containers continue to evolve. The material is ready to move to the next processing phase without haste. 220 to 440 short tons. This is the massive payload capacity of the haul trucks maneuvering through the open pit mines. Why must such an immense volume of earth and rock be moved with such intensity? It only looks obvious to extract ore from the ground, but in reality, the process requires stripping away layers of overburden using hydraulic excavators to reveal the mineral deposits hidden below. This initial clearing prepares the site for rotary drills that penetrate deep into the ore body with absolute vertical precision. Explosives are lowered into every drilled borehole with a calculated weight. The detonation occurs with a millisecond delay to ensure the solid rock formations fracture into manageable fragments rather than being pulverized. One can notice how the dust slowly settles after the blast, exposing the fractured iron-bearing rock ready for collection. Tracked excavators then scoop the heavy material and deposit it into the waiting beds of the haul trucks. The process is only gaining momentum as these vehicles depart the mine for the processing facilities. The journey continues at the primary crushing station. Here, jaw crushers exert immense pressure to break down the raw ore into smaller segments. But this is just the beginning. The material then passes through cone crushers to achieve standardized dimensions. It seems simple to rely solely on mining, but in reality, steel production increasingly depends on a parallel stream of recycled scrap. This source includes discarded household appliances, old automobiles, and dismantled structural steel from various construction sites. Industrial machinery that has reached the end of its operational life is also collected directly on site to be repurposed. Everything only gets more complicated as the scrap enters the preparation phase. One can notice the massive shredders and shears cutting and crushing the metal into uniform pieces. This allows the material to melt much faster once it enters the refining furnace. Why is the scrap crushed into such specific sizes before melting? This precise preparation ensures that engineers can maintain strict control over the blending ratio between the newly produced steel and the recycled components. Transition to the next level. This combination of virgin ore and scrap metal allows the industry to sustain a high output while reducing the total volume of natural resource extraction. The blended material moves toward the heat, marking the conclusion of the raw preparation stage. 150 tons of scrap steel are bundled together and charged into the electric arc furnace to begin the process of material rebirth. Why is the use of recycled metal considered more efficient than smelting raw ore? This method bypasses the energy-intensive reduction of iron oxide, allowing for a faster transition into the liquid phase. The process gains momentum as the sealed chamber is locked, and extremely powerful electric arcs strike down into the metallic mass with a sharp hiss of energy. Temperatures inside the vessel are driven beyond 2,700 degrees Fahrenheit, causing the solid bundles to lose their shape and collapse into a white-hot heap. It only looks obvious that heat alone is sufficient. Within just a few dozen minutes, the entire load of steel scrap melts down completely, transforming into a glowing pool of liquid metal. The camera glides along the surface where lighter impurities rise as slag, floating like a dull crust over the brilliant melt. Automated manipulators then skim these impurities away to ensure the purity of the batch. This is not the limit of the refinement. Engineers fine-tune the chemical composition by introducing precise amounts of carbon and alloying elements such as manganese, nickel, or chromium to achieve specific mechanical properties. The equipment gradually adjusts the mixture, while sensor systems monitor the temperature and chemical balance in real time. At first glance, this resembles a simple mixing process, but in reality, it achieves a level of consistency and uniformity that often surpasses steel produced directly from raw iron ore. The refined recycled steel reaches its peak quality through this constant digital oversight. One can notice the tilting of the furnace as the molten steel is poured into a continuous casting system. The liquid metal flows through a series of water-cooled molds where it begins to solidify into glowing red square or flat steel billets. This transition to the next level requires the metal to reach a specific structural solidity before the next action. Once the required density is achieved, these long, incandescent billets are cut to standard lengths by automated torches. They do not cool down completely, but are transferred directly to the hot rolling line to maintain thermal efficiency. Everything only gets more complicated as the billets enter the reheating phase. Inside the reheating furnace, the temperature is raised to approximately 2,300 degrees Fahrenheit, which is high enough to soften the internal structure of the metal for shaping. One can notice how the glowing billets emerge and pass sequentially through massive rolling mills. Each individual pass compresses the steel further, forcing the material to become thinner and longer as it moves closer to its final industrial form. The process is only gaining momentum. After the heat-intensive shaping, the steel continues into the cold rolling stage. This specific process allows for precise control over the final thickness while simultaneously producing a smoother and more uniform surface finish. It seems simple to just press the metal, but in reality, cold rolling provides the structural integrity required for high-stress applications. The final result of this complex chain is the production of high-quality steel coils. Each coil weighs from several short tons to several dozen short tons, appearing as massive silver cylinders ready to enter the steel drum manufacturing plant. The material leaves the rolling line, transitioning into a calm stage. One steel coil, weighing several tons, is lifted and secured onto a dedicated uncoiling machine to begin its transformation. This automated system gradually releases the metal, exerting constant tension as it unwinds. Why is it necessary to maintain such high tension during the uncoiling phase? If the steel were allowed to slacken, it would lose its alignment on the production line, causing a ripple effect of mechanical errors throughout the entire facility. But the system ensures the sheet is pulled through a series of leveling rollers that simultaneously flatten the surface, removing the coil's natural curvature before feeding the strip onto the conveyor. The process is only gaining momentum. One can notice how the flat steel strip moves with mechanical rhythm toward the industrial cutting station. Here, a high-force blade drives decisively down onto the metal surface with a sharp hydraulic hiss. The blade slices the continuous strip into individual sheets based on dimensions programmed into the control unit with millimeter precision. At first glance, the cutting appears to be a simple repetitive action, but in reality, the quality of these edges dictates the success of every following step. The cutting machine must produce edges that are perfectly straight and completely free of burrs or jagged remnants. This is critical because these two vertical edges will eventually be fused together to form the main seam of the drum body. Even a slight irregularity or a microscopic deviation along the cut can compromise the integrity of the subsequent weld. If the seam is not flawless, the drum may fail to remain sealed, losing its ability to safely contain its chemical or industrial contents under pressure. Everything only gets more complicated as the work continues. Each sheet that meets the strict technical specifications is transferred to a rolling machine. The equipment gradually pulls the flat metal between sets of heavy rollers rotating in opposite directions. It is visible how the rollers compress the steel with carefully calculated force, causing the sheet to curve inward. Under this continuous mechanical action, the edges of the metal draw closer together until the flat strip takes on a hollow cylindrical shape. This rolling process must remain uniform along the entire length of the sheet to prevent any distortion in the final product. A consistent radius ensures the drum body is mechanically strong and perfectly round, allowing it to withstand the physical stresses encountered during transport or storage. The process does not end at this stage. Once the cylinder is formed, an automated resistance welding system creates a continuous seam. The camera glides along the joint where high-voltage currents fuse the metal, creating a seal that is both flexible and sufficiently airtight for liquid storage. This joint is then ground smooth by high-speed abrasive wheels, and the rim is precisely shaped by manipulators to prepare the structure for the next assembly stages. The steel drum body is now structurally complete and ready to move further along the production chain. 6 specialized sets of forming rollers are arranged around the circumference of the drum body as it enters the rib-forming station. Why must the steel surface undergo such intense mechanical deformation at this specific stage? At first glance, the smooth welded cylinder appears finished, but in reality, it lacks the structural integrity required to withstand the immense pressure of industrial storage. This localized pressure from the rollers forces the metal to shift and rise into precisely regulated reinforcing ribs. The process is only gaining momentum. One can notice how the drum body remains perfectly stable, while the specialized rollers apply constant force to the central section of the steel. This ensures that every raised rib maintains a uniform depth of several millimeters and consistent spacing around the entire 360-degree circumference. Every position and the exact distance between these ribs is calculated in advance by engineers to distribute internal forces and external stacking loads. But this is just the beginning. The drum continues its movement through a continuous corrugation rolling system. It is visible how the metal surface transforms into a series of wave-shaped ribs extending along the length of the cylinder. This specific geometry significantly increases the overall rigidity of the structure and reduces the risk of the steel denting when subjected to impacts during transit or when stacked in multiple layers in warehouses. The raised rib structure provides practical advantages that extend beyond simple reinforcement. These protrusions allow the heavy drum to roll more easily across floor surfaces by reducing the contact area and improving grip for manual handling or lifting equipment. Because the formation of these ribs directly dictates the durability and safety of the final product, this transformation is regarded as one of the most critical stages in the manufacturing cycle. The steel drum is now reinforced and ready for the next phase of assembly. 100% of the lids and bottoms for industrial steel drums are manufactured in parallel with the main body to ensure perfect synchronization of the assembly line. Why is the production of these flat components just as technically demanding as the cylindrical shell? It only looks obvious that a flat surface is easier to handle, but in reality, the structural integrity of the entire container depends on the precision of these two circular plates. Industrial stamping presses receive square sheets of raw steel at high speeds. One can notice how automated feeders align each sheet before powerful hydraulic clamps lock the material firmly between an upper punch and a lower forming die. The punch descends with a sudden, deafening impact, exerting hundreds of tons of force over a fraction of a second to drive the metal into the mold. It gets more complex further on. Each individual stamping cycle is completed in less than 5 seconds, but the machine must regulate the pressing force with absolute precision to avoid micro cracks or unintended deformation in the steel grain. The lids and bottoms are still not considered finished components once they are separated from the primary sheet. Their outer edges are immediately transitioned to an edge rolling station. One can notice the equipment gradually bending the steel rim as specialized rollers curl the perimeter into a specific predefined profile. This curling process serves a dual purpose by significantly increasing the structural stiffness of the part while creating the necessary contact surface for the final airtight seal. Any unevenness in the rolled edge or a slight deviation in the curvature radius will directly compromise the sealing performance and the overall durability of the finished drum. The process is only gaining momentum as top lids designed for filling require additional precision machining. Automated drills or stamps create fill openings at coordinates calculated down to the millimeter. Following this, steel-threaded collars are pressed into the holes to provide a secure interface for industrial plugs. These threaded systems must achieve a perfect fit, maintaining a seal tight enough to prevent hazardous leaks, while remaining durable enough to survive hundreds of opening and closing cycles. One can notice how the lid remains perfectly flat, even after the collar is installed, showing no signs of warping or structural fatigue. The equipment ceaselessly repeats these coordinated operations to guarantee that every component possesses high dimensional accuracy and a uniform thickness across its entire diameter. Each lid and bottom is specifically engineered to withstand internal pressure, external impacts, and the crushing weight of stacked loads during long-distance transport. This sequence of manufacturing steps ensures that the drum remains robust and safe throughout its entire operational life in harsh environments. The finished components move toward the assembly area, where they will eventually meet the drum body. Thus, the transformation of raw steel into high-strength structural parts reaches a conclusion, preparing the material for its final integration. 100% of the steel drum bodies must pass through a rapid washing and anti-corrosion treatment system before they are permitted to enter final assembly. Why is such a meticulous chemical cleaning required at this specific moment? High-speed machining and forming processes leave behind a persistent layer of lubricants and microscopic debris. Without total elimination of these residues, the final protective coatings would fail to adhere, leading to structural degradation over time. Industrial spray nozzles blast the metal surfaces with specialized chemical solutions to strip away residual oils and fine metal dust. One can notice how the liquid sheets off the cylindrical walls, carrying away every trace of surface contaminants. But this is just the beginning. The drum body, lid, and bottom meet for the first time on a single unified assembly line after being manufactured in separate specialized zones of the facility. It is visible how high-precision industrial robots or skilled technicians position the lid onto the open end of the cylinder with millimeter accuracy. It seems simple to place a cap on a container, but in reality, even a microscopic misalignment here compromises the hermetic performance of the finished product. The process is only gaining momentum. Automated conveyors transport the assembled components into a heavy-duty rim rolling machine. Once the lid and bottom are seated, steel rollers begin to apply substantial mechanical force, compressing and flattening the edges that were pre-rolled during the earlier stages of fabrication. This intense pressure creates tight sealing ridges, known as chimes, that encircle the top and bottom rims with absolute uniformity. These chimes function as the primary structural lock, fusing the lid and bottom to the body to ensure the unit can withstand significant internal pressure. It gets more complex further on. Because these ridges are the only barrier against leaks, their geometric perfection determines if the drum can safely transport hazardous industrial liquids without failure. Sensor arrays and automated inspection systems operate without interruption throughout the entire duration of the assembly sequence. The equipment gradually scans for roundness, edge deformation, and exact geometric alignment to verify that no deviations have occurred during the rolling process. Everything only gets more complicated as the speed of the line increases, yet the sensors maintain a continuous vigil over every critical parameter. Therefore, every steel drum is subjected to triple-check validation to confirm it adheres to strict industrial standards for sealing integrity and operational safety. One can notice the smooth, reflective surface of the finished rims as they exit the final station. The metal leaves the assembly zone, transitioning into a calm stage of final preparation. One temporary protective cap is manually fitted onto the drum opening before the painting stage begins. Why is this small plastic component so critical to the entire manufacturing cycle? The interior of the vessel must remain completely sterile to avoid the rejection of the final product. A single grain of dust or a drop of moisture entering the open orifice would contaminate the internal surface, rendering the drum useless for sensitive chemical storage. Automated conveyor systems transport the steel drum into a fully sealed painting facility. One can notice how multiple spray nozzles move in synchronized patterns across the cylindrical surface. These nozzles oscillate with calculated precision, applying an even and controlled coat of liquid paint across the entire exterior. It seems simple to coat a metal surface, but in reality, the thickness must be uniform down to the micron to ensure the integrity of the layer. This paint serves as a primary technological shield rather than an aesthetic choice. It acts as an additional protective barrier that blocks oxygen and humidity from reaching the steel, preventing the onset of corrosion during long-term storage in harsh environmental conditions. The process is only gaining momentum. Thermal sensors monitor the next phase as the drum advances slowly into a high-temperature curing oven. Heat and exposure time are tightly controlled by computer systems to ensure the polymer chains in the paint bond correctly with the metal. One can notice the subtle change in the surface texture as the heat hardens the coating into a durable shell. Once the curing process is complete and the temperature stabilizes, the temporary protective cap is removed, marking the conclusion of the coating cycle. The drum is now prepared for the final technical inspection. Approved steel drums move toward the finished goods warehouse once they pass every quality control checkpoint. And this is not the limit of the logistical chain. Automated manipulators or warehouse staff neatly stack the vessels onto wooden pallets in specified quantities. This arrangement is designed to ensure maximum stability during high-intensity handling and stacking within the storage zone. Depending on the specific transportation requirements of the client, the pallets may be wrapped with layers of transparent protective film or secured with heavy-duty tension straps. This prevents any shifting or movement during transit. When shipping orders are officially released, forklifts load the pallets onto heavy trucks or sea containers. One can notice the smooth movement of the loaders as the drums leave the factory gates to enter the global logistics network. From regional distribution warehouses to international seaports and major logistics hubs, the journey of each steel drum continues quietly across continents. The manufacturing process ends here, but the industrial life cycle of every drum is only just beginning. Thus, the steel reaches the standard ready for the further stage of its global service. 100% of the global supply chain relies on the structural integrity of the humble steel drum to prevent catastrophic leaks and environmental damage. Why is this specific cylindrical form favored over all other storage solutions? At first glance, the container appears to be a basic metal shell, but in reality, it is the result of a highly sophisticated engineering process where precision is non-negotiable. Materials are strictly regulated from the very moment the raw steel sheets enter the production facility. One can notice how automated sensors verify the thickness of the metal with micron-level accuracy to ensure it meets international safety standards. It is visible how the high-speed rollers curve the steel into a perfect cylinder, preparing the edges for a critical joining phase. But this is just the beginning. Engineers monitor the longitudinal welds ceaselessly to ensure there is not a single microscopic gap in the seam. The equipment gradually applies pressure and electric current to fuse the metal into a single unified structure capable of withstanding extreme internal pressures. Everything only gets more complicated as the drum transitions to the end capping stage. Rigorous safety standards dictate that every component, from the reinforced rolling hoops to the precise threading of the bung holes, must follow an exact mathematical blueprint. The process is only gaining momentum. Each unit undergoes a series of pneumatic tests where high-pressure air is injected to detect even the smallest drop in pressure. The camera glides along the automated finishing line where protective coatings are applied in a perfectly even layer to prevent corrosion from chemicals or food products. It seems simple to produce a container, but in reality, the smallest margin for error in the seal could disrupt global logistics and energy supplies. Steel drums serve as a silent yet indispensable link in the modern industrial world. These containers form the mechanical backbone that allows global supply chains to operate safely and without interruption across every continent. The manufacturing cycle concludes this phase, ensuring that the finished product is ready for heavy-duty service in the harshest environments. Thus ends one of the key stages of industrial packaging production.